Welcome back, everyone. The effort to establish a permanent human presence on the moon has reached a major milestone with the testing of lunar oxygen extractors. These prototype systems are designed to harvest breathable oxygen directly from the moon's regolith, the layer of fine dust and rock that covers its surface. Instead of relying on Earth-based resupply missions, future lunar bases could use these extractors to provide life support, fuel oxidizers, and industrial feedstocks by processing local materials. Scientists are testing thermal and chemical methods to isolate oxygen from minerals like ilmenite, which is rich in oxygen-bearing compounds. Early results from Earth-based lunar simulants suggest that consistent oxygen yields are possible using solar-powered heating or molten salt electrolysis. These technologies are being refined by multiple research groups to ensure they function reliably in the harsh conditions of the moon. If proven viable, these extractors will play a crucial role in making lunar settlements sustainable, scalable, and independent from constant resupply. Lunar oxygen extraction systems begin by collecting regolith, the loose layer of dust and crushed rock that covers the moon's surface. Robotic excavation units or human-operated loaders gather this material and transport it to the processing unit. Regolith contains a variety of oxygen-rich minerals, especially ilmenite, which is composed of iron, titanium, and oxygen. Although the oxygen is tightly bound in these mineral structures, it can be released through specific thermal and chemical processes. The extracted oxygen could eventually support human life and serve as a vital component in fuel production. One common approach under testing involves thermal reduction, in which regolith is heated in the presence of hydrogen gas. At elevated temperatures, typically around 1000 degrees Celsius, the hydrogen reacts with oxygen atoms in the ilmenite to form water vapor. This vapor is then collected and passed through an electrolysis unit, which splits the water into hydrogen and oxygen. The hydrogen is recycled back into the reactor, while the oxygen is stored in pressurized tanks. This method has been proven in lab conditions and is now undergoing stress testing in lunar analog environments. Another promising method being explored is molten salt electrolysis. In this approach, regolith is mixed with salts and melted into a slurry using concentrated solar heat or electric heaters. Electrodes are inserted into the mixture, and an electric current is passed through it. This causes the oxygen to be released at the anode, while metals such as iron and titanium are deposited at the cathode. The system avoids the need for hydrogen gas and can produce useful metal byproducts as well as oxygen. Because of its dual output, this method is especially attractive for long-duration missions. Regolith must first be processed to remove large debris and prepare it for extraction. Screening and grinding systems are used to ensure the material is of uniform consistency before being loaded into reactors. Automation is a critical component of this process, as lunar operations will likely run without constant human presence. Robotic systems are being designed to coordinate regolith delivery, monitor reactor temperatures, regulate gas flow, and detect system malfunctions in real time. Redundant control systems and fault tolerance measures are also being tested. Oxygen captured from these systems must be stored safely and efficiently. Engineers are developing pressurized tanks and cryogenic storage solutions that can hold large volumes of oxygen for later use. The oxygen may be used directly for breathing in crewed habitats, or as an oxidizer in fuel mixtures for lunar ascent vehicles and deep space missions. Efficient storage is particularly important on the moon, where regular resupply from Earth is costly and limited. Some prototypes include distribution lines connecting multiple habitat and fueling nodes. Energy supply for the extractors is another crucial factor. Solar power is the most likely option, given the abundance of sunlight on the lunar surface during the 14 Earth-day-long lunar day. Solar panels will supply electricity to power heating elements, control systems, and compressors. Energy storage systems, such as lithium-ion batteries or fuel cells, are used during the long lunar night when solar power is unavailable. Some concepts include compact nuclear power units to provide a continuous power source regardless of sunlight conditions. Because dust is a major operational concern on the moon, oxygen extractors need to be designed to resist contamination and wear. Regolith particles are sharp and electrically charged, which causes them to stick to surfaces and penetrate seals. Equipment must include protective shields, dust-repellent coatings, and pressurized enclosures to prevent dust from entering those sensitive components. Filters and cleaning cycles might be incorporated into material transport systems to remove excess dust before it reaches the reactor inlet. Communication between extraction units and mission control must be reliable for successful remote operation. Each system will be equipped with sensors to monitor temperature, pressure, chemical composition, and structural integrity. These sensors feed into onboard processors that can make real-time decisions or transmit data to a command center for review. Autonomous software will be used to detect anomalies and adjust operations without needing constant human input. The long communication delay between the Moon and Earth makes such autonomy essential. In the future, lunar oxygen extraction systems could become fully integrated into permanent moon bases, operating continuously to support human habitation, agriculture, and spacecraft refueling. Advanced versions of these systems may include modular reactors that can be moved to different sites based on regolith composition, with smart sensors determining optimal locations for maximum yield. As technologies mature, these extractors could supply not only oxygen, but also raw materials for construction, such as metals and glass derived from the same regolith input. This would reduce the need for Earth shipments and enable self-sufficient lunar industries that operate around the clock using autonomous robotic teams. Looking farther ahead, oxygen extraction infrastructure might serve as the foundation for interplanetary logistics. Bases on the Moon could produce and store large quantities of liquid oxygen and hydrogen, creating orbital depots for spacecraft traveling to Mars or beyond. Oxygen extracted from lunar regolith could power return missions, emergency supplies, or deep space tugs. Coupled with in situ fuel production, this could drastically reduce mission costs and enable regular travel between planetary bodies. As part of a broader off-world economy, lunar oxygen could become one of the first true extraterrestrial exports, establishing the Moon as a critical node in space exploration. If lunar oxygen extractors pass the next phases of testing, they could become a cornerstone of future space infrastructure. Once deployed on the Moon, they would support not only crewed habitats, but also robotic refueling stations, in situ manufacturing plants, and launchpad operations for missions deeper into space. Long-term ambitions include coupling these extractors with automated excavation systems and solar furnaces to create full-scale lunar processing units. This would mark a shift from exploration to true habitation, where resources are harvested and used directly on the Moon. As costs fall and testing continues in simulated lunar environments, these oxygen systems may be among the first tools humans deploy permanently beyond Earth. Their success would demonstrate the practicality of space-based resource utilization and pave the way for off-world industry. The Moon would no longer be just a destination, but a launchpad for humanity's next chapter in the solar system. Thank you very much for watching. Please like and subscribe.